So I hope I convinced everybody that quantum mechanics is an example of one-dimensional quantum field theory. And now, well, now we have two field theories. One is classical Lagrangian mechanics. Three, actually. We have the Hamiltonian formulation of classical Lagrangian mechanics. And now we have one-dimensional quantum field theory that's quantizing these theories. So let's make a connection between quantum mechanics and classical mechanics. So in other words, let's see what happens with quantum field theory as h goes to 0. So before I'll do this, let me recall that there is something that is called the momentum operator and something that's called the coordinate operator. So this is just a derivative with respect to QA, and this is the operator that multiplies function by QA. So now consider states, pure states, with the wave function of a form f of q over h, and then some phi 0 q. And let's see how the expectation values of these operators behave with respect to when h goes to 0. So p a c. So this is the integral over rd. Phi 0 q absolute value squared. Then we have the df dqa dq plus terms of order h.
You think that this is an operator, the f of q, or
no, it's a
or
function.
Just a function. Just look at something like
smooth
this.
Function.
Okay. Okay. Fine.
So we consider the so now h is a parameter which is physicists would criticize for this because h is not a parameter, it's a constant, it's a fixed constant. But of course the meaning of this limit is that we set all other values of in the theory like mass, the potential, to the infinity, so that in the relative scales this constant goes to 0. So this is what's meant here. And then QA on this state, it's the expectation value of Q with respect to this probability measure of the configuration space. So if we okay, so now let me recall something that we didn't discuss: states in classical mechanics. Classical Hamiltonian mechanics. So states in classical Hamiltonian mechanics are simply probabilistic states on the configuration space. So it's the they are positive, normalized linear functionals, or let me just say it like this: they are probabilistic measures on the configuration space, on T star D in our case. So, for example, such measures can be defined by a density. So an example would be rho d. function such that the integral over d star rd rho dp dq is equal to 1. Example 2, we can have some submanifold, and we can have a probabilistic measure supported on this submanifold. So we can have the rho L such that when you integrate the function against this measure, this is simply the integral over L, the restriction of the function on this submanifold, some density, and then the measure on this submanifold induced by the Euclidean measure on R2D. So the question is, so if we consider this family of states, what will be the limit as h goes to 0? Will it converge to some state in classical mechanics? Well, clearly it will, and it will. So this state C converges as h goes to 0 to the classical state with the density which is supported on this Lagrangian submanifold in T star D. And on the Lagrangian submanifold, the density is given by the absolute value squared of phi0. And so this is an example of a semi-classical state in quantum mechanics. And then if you have observables, quantum mechanical observables, you take the expectation value with respect to over this state, and then as h goes to 0, it will converge to the integral over L, where p is equal to df dq. So the observables are Hermitian differential operators. They have symbols, which are functions symbol of A, function on T star D, and so
basically you're giving an interpretation to what this means.
Yeah, exactly. So any observable will converge to the expectation value of the corresponding symbol with respect to this probabilistic measure on the configuration space. This is the semi-classical limit in terms of states. So now we may ask, okay, so this is what happens with the states, and now what happens with the propagation of states? So in other words, we may wonder what is the limit of the kernel of the propagator as h goes to 0. And it doesn't have a limit, but it does have the asymptotical expansion. So it is asymptotic to some expression. I will give a statement. The proof of this statement is a homework exercise. The answer for the semi-classical expansion. So theorem. Before I formulate this theorem, I just want to remind that, well, we have the Schrödinger operator, or quantum Hamiltonian, which is minus h squared delta over 2m plus v of q. The corresponding classical Hamiltonian, of course, it's p squared over 2m plus v of q. It's the symbol of this differential operator. You just have to, in the symbol h, I, h, d, dq is replaced by the So the semi-classical behavior of the propagator will be described in terms of the classical dynamics for this Hamiltonian system, but this Hamiltonian system can also be written as a Lagrangian system with the Lagrangian m over 2 xc minus v of q. So I will show how to describe the asymptotic of the, I will give the answer for the description of the asymptotics of this propagator in terms of the Lagrangian dynamics with this Lagrangian. So theorem, so suppose that points q1 and q2 are connected by solutions to the Euler-Lagrange equation for L, C, Q, and there are finitely many of them. I will denote them gamma C tau, where tau goes between 0 and t. So connected by solutions in the interval, in the time interval from 0 to t. So that gamma C 0 is q1, gamma C t is q2. Then ut q1 q2 is asymptotically equivalent to sum over these classical solutions 2 pi I minus the dimension over 2 exponent I over h classical action computed at this solution plus I pi over 2 the Morse index of this trajectory, and then the determinant of the matrix of second derivatives of this with respect to q1 and q2, square root of it, and then 1 plus sum over powers of power series in H. So this is simply the result of the so how to derive this answer? Well, you have to solve the Schrödinger equation. Schrödinger equation is a differential equation for this function, and you just have to find the asymptotical solution to the Schrödinger differential equation which satisfies the initial condition. So that would be very easy, but the problem is that here in this asymptotical expansion t is much bigger than h. So first we take the limit as h goes to 0, and t is finite. So we cannot use the initial condition in this formula. So we can only use the Schrödinger equation, but this equation will not define completely the solution. But it turns out that this condition, properly understood, actually defines this whole power series. So it determines solution. And in fact, even stronger statement holds. If you just there is a unique solution to this functional equation for the kernel. There is a unique asymptotical solution in the class of functions sum over gamma c e to the s gamma c over h, and then any function q1, q2 and power series in h.
Yeah, so given the class.
Given this most singular part, the rest is determined uniquely. All this square root of 2 pi's, everything. So that's the so this I should say that I was looking for this theorem in textbooks, so it seems like this is some kind of fundamental fact about semi-classical analysis, but I didn't find any statement. So I gave it to this problem, this conjecture to work on to Theo Johnson-Freud, whom some people here know. He's a student in Berkeley, and he proved this theorem. So it's a very nice fact. Just think about what it means. It means that just using the gluing axiom and the fact that there is this singular term in the semi-classical expansion of the amplitude, which is given by the classical action, just these two facts define completely the asymptotical expansion of quantum mechanical propagator. So this is the so this is one of the motivating factors for doing the proof, for defining the functional integral in the semi-classical fashion.
Just a quick question about the asymptotic expansion of ut. Is there a 1 over in the determinant?
No.
No, it's a square root
just
of the absolute value of the determinant. Not a 1 over.
No. You would think of 1 over, but it's a square root. It's just like the torsion.
Because we've seen the 1 over every time now when we've done the asymptotic expansions in the oscillatory intervals, right? We have gotten a 1 over every time.
And there's not a 1 over in
yes. So let's just wait.
Yeah.
So we will have the asymptotical expansion now of the oscillating intervals.
No, but you see, so you're, this is kind of way to, this is replacement for the Schrödinger equation.
This is, in particular, this is a replacement for the Schrödinger equation.
Asymptotically.
Yes, asymptotically.
Yeah,
You see, the Schrödinger equation gives you quite a lot of information about this power series, but it doesn't determine completely, for example, these constants. You just cannot fix these constants from the Schrödinger equation because it's a homogeneous equation. the initial condition is not homogeneous. But you cannot use the initial condition because you cannot set t to 0. It will be outside of the realm of this asymptotic
No, I'm
expansion.
confused. I thought that quantum mechanics somehow determines classical mechanics, but you say there's some factors. I mean, I thought if you have the Schrödinger equation, then you can just go to the limit and you would obtain classical mechanics.
No, you also have to have some initial conditions. Schrödinger equation is a linear homogeneous equation. It's like in linear algebra. If you want to fix a solution to a linear homogeneous system, you have to fix something.
Yes, okay.
So like, if you have a Schrödinger equation, you have, if you want to have a specific solution, not a family of solutions to the Schrödinger equation, but a specific solution, you have to fix an initial condition.
Fair enough.
That's like classical mechanics. We also have to fix
It's like classical mechanics, yes. If you don't fix the initial conditions, you will have a family of solutions, but you will not know which one to choose.
Okay. I'm still a little mystified, but let's.
Well, no, let's
Let's go on.
okay, let's go.
Tell me, this theorem is just about formal power series, or also it can be
It's
explained
only
more.
about formal power series. Yeah. It's about the asymptotical solutions. Maybe there is another theorem. Not only about formal power series. I don't know.
So I mean, it's possible that we could recover the Schrödinger equation completely from this, or
In formal power series, Schrödinger equation follows from here.
yes, but you said that it possibly has an even stronger theorem when you at analytic, where you could sum those power series.
Possibly there is a stronger statement of the nature of something like this nature, that there is a unique analytical solution to this gluing property which satisfies also the Schrödinger equation with this asymptotical behavior as h goes to 0.
But remember that we can always have these asymptotically small terms, right, with other bases and so on.
But this is a very strong condition.
That's true.
So I don't know. I mean, the theorem is for asymptotical expansions, formal power series. So it's a very strange fact that semi-classical expansion is completely determined by and just completely determined by the classical action.
Okay, so I mean, usually you say it. So you have a quantum system. I mean, quantization. You usually think of this as some kind of choice, but you're saying that's not my choice, really. I mean, the classical system, in some sense, determines the quantum system. No?
In some sense, well,
I mean, at least.
Well, this is in quantum mechanics where we fix the quantization.
Yes.
yeah.
No, but
Well, you see,
I mean, you start with. So this is a classical.
I'll
Yeah,
tell
that's
you.
true.
No, there is an ambiguity. I mean, it's not true. It's not correct to say that there is no there is a uniqueness of passing from classical to quantum.
Yeah. I mean, it's almost set.
This convolution is a measure on Rn. I assume that this is the Euclidean measure. But you can change it by any formal power series that starts with 1. And then the solution will be different. You fix the measure, there will be a unique solution here. So in some sense, the ambiguities in quantization, there are ambiguities in this convolution measure. That's one of the interpretations. Okay. So, more comments? I think it's fairly late, so the more of this discussion we'll have, the more relaxed it will be. So, but let me come to final. I didn't finish So according to his proposition, this propagator somehow has this meaning. You integrate over all parameterized paths from Q1 and Q2 with this weight, with some mysterious measure. So if it's not an oscillating integral, if it's e to the minus s, and if s is bounded from below, then it's a linear integral that exists in probability theory. You can define it really analytically. This one is hard to define, but you see, on the other hand, we have a very strong statement about semi-classical asymptotic. So, and on the other hand, we have the formula that expresses the semi-classical limit of finite dimensional integrals of this nature as the sum over critical points. Critical points of the action are exactly this gamma c. And then I'll just write what was repeated so many times yesterday. So e to the value of the function at the critical point plus I pi over 4, the signature of the quadratic part of the expansion of the function near gamma c, divided over the determinant of the quadratic part, absolute value, and then 1 plus sum over non-zero, non-trivial graphs, IH to the power minus the Euler characteristic of gamma divided by the order of the automorphism group FC of gamma, where FC are these finite diagrams that we were discussing last time, but last time they were finite dimensional, now they are infinite dimensional. So let's see, let's make sense out of this expression. So remember, in the finite dimensional case, we'll make sense out of this expression next time. I know, I'm lecturing until 4. Yeah, so we still have 15 minutes. Good. So, in the finite dimensional case, well, we had a prefactor, I to the n over 2, and then we had this signature factor, I to the pi over 4, the signature of the matrix B, which is e to the I pi over 4 n, e to the I pi over 4 and plus minus and minus. This is the number of positive eigenvalues, and this is the number of negative eigenvalues. But now n plus plus and minus is equal to n. So I can write this as e to the I pi over 2n times e to the minus I pi over 2 n minus, where n minus is the number of negative eigenvalues. Okay, so n is infinite in our case. And now I claim that n minus is something meaningful. And plus, minus, and minus cannot be meaningful because there will be infinitely many positive eigenvalues. So let's look at the variation of the action. So suppose that let's suppose that we have a path which is different from the classical path gamma c by some delta gamma. So then this is equal to s of gamma c. The linear terms will vanish. So From the quadratic terms we will have delta gamma squared d tau, and then we will also have the integral from 0 to t 1/2 v double prime of gamma c tau delta gamma tau squared d tau minus sum over n greater or equal than 3 1 over n factorial integral from 0 to t nth derivative of v at gamma c tau delta gamma tau to the n d tau. So the quadratic term, and then also the endpoints of this path should be q1 and q2. So with the endpoint of gamma c are q1 and q2. So at the endpoints this delta gamma should vanish. And the quadratic term can be written as 1/2 integral from 0 to t delta gamma tau, and then when you integrate by parts it will be minus second derivative in tau minus second derivative v double prime gamma c tau delta gamma tau d tau. So this is our KC. That's the operator responsible for the quadratic part in the action. Now you can see that it's minus the second derivative in tau and then some smooth perturbation. So this operator will have infinitely many negative eigenvalues and infinitely many positive eigenvalues. We can let's consider potentials reasonable enough so that there would be no some kind of pathologically infinitely many negative eigenvalues. So that shows that what we have to do is we have to forget about this because our constant is not determined yet. We should put minus pi over 2 and then the number of negative eigenvalues of Kc. And then it's defined. So this is also defined. And it coincides with what we have from the semi-classical formula. The only thing that we have to check now is that the Morse index of the classical trajectory is equal to the minus the number of negative eigenvalues of Kc. And remarkably, it's a non-trivial fact, but it's also not. It's a non-trivial theory. So there, I will give some reference. So actually, there is a reference in the textbook. There is a recent book by Tartajan on textbook on quantum mechanics, which is oriented for math graduate students, and he has a proof of this theory, or at least the explanation of this theory.
And mu was, so we have this curve with these two endpoints?
Mu is the Morse index, so it's
The Morse index.
yeah, it's the number of the say if this is the it's the number of tangencies that are parallel to the initial Lagrangian.
Okay. So we're fixing some Lagrangian as the boundary condition now.
Yes, we're fixing the Lagrangian Q1
Yeah,
and
and
Q2.
Q2. Okay.
Yeah.
Right. Okay.
Okay, so this is the statement, but then we have the
Gamma is what? Gamma is a path.
gamma
Is
is
a path in the case space.
gamma is a path in the configuration space, but then gamma dot gamma is the path in the tangent bundle, but then it's Rn, so it's also a path in the cotangent bundle. So it's just a parameterized path leads to tangent bundle.
Trying to figure out why it's not single. But is it clear how it may happen that this picture is?
Well, as t moves, you can move back in position, right? It's not a generic situation if q is high dimensional, but if the configuration space is one dimensional, this would be a generic situation.
Ah, you just forget about T. So you project everything on
Harmonic oscillator.
No, the curve t runs in qp space, right?
Yeah, but well, yeah, you don't consider T as another.
This is a
I see.
PQ.
I see, just PQ, and you project along
Yes, and
along the T axis. Yeah.
you project along the P axis.
P axis, but yeah, this is a curve. Yeah, there's no graph. P of Q of T, but just the curve.
Yeah, just the curve.
Okay.
It's not the graph.
Sorry.
Okay, so this is okay. Remarkably, this is okay with the semi-classical degree. Now we have this determinant. It's a determinant of the differential operator. Well, as is, it doesn't make sense, so we have to regularize it. By regularization, I mean the following. There are many ways to do it. So here is one way to do it. Say, suppose that you have an operator of the form k0 plus v, where k0 is some simple differential operator, or just some simple operator, like this one. So you might say that instead of computing the determinant of this operator, which doesn't make sense, I will compute how the determinant of k0 changes when I'm switching on this perturbation. In other words, so what I want to compute is the determinant of the ratio of these operators. So if it's the determinant of k relative to the determinant k0. You see, then it will be this operator. And then, in many good cases, this is a Fredholm operator, so its determinant is defined. So this is one way to do it. And the other way is so-called zeta function regularization of differential operators. It's another way, but I don't want to go into the details of this. I just want to say that, so that's one way. The other way is zeta regularization. All I want to say is that there is a reasonable definition of what the regularized determinant is. And then there is a theorem, which is...
So this gamma, you have this critical point, this is a solution to the classical equation.
Yeah.
So you start by looking at all classical ways to pass from P to Q.
Mm-hmm.
And then you show them you associate the Morse index.
Yeah.
Yeah, okay, and that's...
And that's it, exactly the number of negative
Yeah.
eigenvalues. Okay.
Yeah. And you really say, yeah, the positive directions do not matter. That sounds reasonable.
No,
Well, we assimilate them in this constant. We're going to figure out
this infinite dimensional constant, so I don't want to think about this constant yet.
So that's also the reason. I mean, you have this factor e to minus
Yes.
I times half.
Yeah.
So
Yeah.
this could give something which is far away. Okay.
So far I'm doing something really sort of almost stupid. So I take the recipe for the finite dimensional asymptotical expansion of oscillating integrals, and I'm substituting the gadgets that come from this from this idea into the formula that we derived yesterday. And I'm just comparing the coefficients between this conjectural answer and the answer that you can actually prove from the Schrödinger. And remarkably, I'm discovering that not only the leading terms agree, but this agrees, and then another.
And here comes the explanation for 1 over and not 1 over.
Exactly. So the absolute value of the determinant of the Hessian of the Hamilton-Jacobi action, the value of the action function on the classical trajectories is called Hamilton-Jacobi action. This is equal to 1 over the absolute value of the determinant of Kc. And if you will take into account this statement and the fact that mu is more or less the number of negative eigenvalues of this matrix, then you can erase the signs of the absolute value. So this is another non-trivial fact, but remarkably it holds. So then there is a question, whether it's true or not that the power series given by finite diagrams and the recipe for the finite diagrams is just the same as before.
So this, the determinant on the left side, this is just a finite determinant.
This is the finite determinant, and this is the regularized determinant.
Yeah, but the other thing, this is something much more complicated.
Yeah.
Yeah.
With the appropriate regularization, this equality holds.
Yeah.
So, to be continued tomorrow.
No.
Possibly.
So I just want to make an announcement about next lecture. So next lecture will be on Tuesday, and Volodya agreed to make a sort of entr'acte for me. He will talk about another classical gauge theory, which is remarkable by its mathematical appearance, and also it's absolutely fundamental by its physical meaning. So he will talk about Einstein gravity. As a classical gauge theory. So this is the subject for Tuesday. And then on Wednesday, we will continue with the semi-classical quantum field theory.